So this is third week, and we are going to cover the topic that is the some of the portion of the blockmesh is still left. Although Abhishek has covered in the started class, and he has asked tell about that how blockmesh is created and how you can create a cylinder, and what is the check mesh, how can you check your quality of the mesh, so what is the non-orthogonality and what is the skewness. So these things subjects to talk in the study class. Today we have some topic is left, that is the multi-grading, and what is the simple means how you can do the non-uniform meshing. So generally when you create the use the block mesh, you create the hexahedral dominant meshes. So all cells has been divided into the blocks. That is why it is called as the block mesh. Okay. But if you want to create the non-uniform mesh, so then there is a technique that is the multi-grading that we are going to discuss, that can be used to create the non-uniform meshes. So like while you are using the turbulence model, so then near the walls it is required the finer mesh should be available near the wall. So in such scenario, this simple grading concept is can be utilized. Also, we are going to see that what is the finite value method and how you can discretize the Navier-Stokes equation and the continuity equations using the finite value method. Also, we are going to discuss this two algorithm, that is the simpleFoam. Also, I am going to discuss the PISO foam, and then finally we will go to the pimpleFoam. So these things we are going to discuss today. So this image I have taken from the means OpenFOAM user guide. So you can just type on the terminal OpenFOAM blockMesh. So you can just visit this site here. Everything, some brief about every concept about the blockMesh is given here. Okay. So even the complex geometry you can create using the blockMesh if you use little bit trick. So for example, while I was working on a breeder blanket concept, so first I tried to create the mesh using the ANSYS software, but I was not getting the hexa dominant meshes. So for that project, I have used the block mesh. I means although I have to work for 4 or 5 days continuous, and I was able to create means a very complex geometry using the block mesh. So very complex geometry can be created by using the block mesh utility, although you have to give some times, but once you create it, then you can means you can use that means that is going to work well compared to the by default message that you create by using other commercial software. So it is means you can master your block mesh quality. So this image I have taken from the that site that I have shown you. So simple grading, generally there you find that 1 1 1. So it means that in 3 direction, that is x y z, you are giving a means uniform grading. Okay, so when you type 1 1 1, then in all the direction you are specifying that the cell spacing will be distributed very uniformly. But if you want to create a non-uniform message, then this simple grading, this expansion ratio you have to specify. So what is this formula? That this is the end cell upon this is the last start cell. So the ratio of the end cells, the means the size of the end cell upon the size of the start cell is equal to the expansion ratio. Okay, so it means that if you are specifying here 2, okay, it means that the cell size that is given here, that is the del E, upon the cell size that is given here, that is the del S, is equal to 2. And now if you are specifying equal to 3, it means that the size of this cell upon the size of this cell is equal to 3. So this is something related to the expansion ratio. Now if you want to specify that means this cell size is larger compared to this cell size, then this ratio 1 you can define, you can just type here 0.5. So 1 by 2 equal to 0.5. So in this manner, you can play with this, and you can create the non-uniform meshes. Okay. Now, if you want that this kind of, suppose you have a one block and you want that here also there is a simple means grade spacing should be available here. This side also should be available, and this side also available. So this technique, either you can use that, you can create four different blocks. So suppose you have a one block, okay, and you want to create the simple grading, like multi-grading in all walls, means all four walls you want to create grading, as you can see in the image. Okay, so either you can use the block, four blocks, and then you can use the this technique that I am specifying here. For each block you can use a simple grading, and in this way, like you can specify 1, 2 or 3. In this way you can give the this simple grading, this kind of technique. Okay, so this is one way that you can specify, that you can create the different four blocks, and on each blocks you can give the grading system. But other there is another technique that we are going to talk. I am going to show you an example that is known as the multi-grading. Okay, so I have created one folder. Sorry, I should also have uploaded on the. I always forget that. I will share the Excel sheet in the WhatsApp group. So that blockMesh I'm just uploading here. You can start working with me. So there I have given two folder, that is the dynamic mesh. So yesterday Abhishek was little confused about how to create a dynamic mesh. Okay, so this is the syntax for the blockMeshDict. So blockMeshDict is a dictionary, and here that you are seeing at a different level, that is known as a sub dictionary. Okay, so this convert to meters, that is given equal to 1. It means that it is currently you are working on the meter system. Okay, so whatever the dimension that you are specifying here, that is 1. It means that 1 meter. Okay, so if you want to work in the centimeter or millimeter, then you can just convert, just you can divide by 1 by 100 or 1 by 10 based on the unit system you want to work on. Okay, it is also possible that if you were suppose you are doing some scale analysis kind of the project. Okay, so it is not necessary that you are working on just a millimeter or centimeter. Suppose first you have done some project on a scale level equal to 1. Now you want to do some project on the scale level 1 by 2, means that is the every dimension is 1 by 2 of the that model project. Okay, so in that scenario you can just write here 0.5. Okay, so this way you can just do the, means you can scale down, or you can scale up the given dimension or given meshing in this blockMeshDict dictionary. This is way of the defining the different dimension or different variable. Okay, this is the delta x that is going to be used for the creating the different cells. Okay, and this is, suppose you want to find out what is the length in the x direction, and if you want to find in the length in the y direction, if you want to find in the length in the z direction. So this way you can also use the calculator kind of the syntax in the OpenFOAM. Okay, so if whatever the expression you want to calculate, that you have to put in the semicolon. Okay, so this way you can see here, this way you can calculate the length in the y direction, and this way you can calculate the z direction. Now if you want to know that how many cells you want to specify in the x direction, y direction and z direction, so that is here, that is there, done here. Okay, so here we are not fixing the number of cells, here we are fixing the delta x. Okay, so like if you want to fix that minimum cell size in the x direction should be 0.05 mm. So based on this delta x, it is going to calculate the number of cells in the x direction, and that x cells, that variable that you are creating here, that is going to be specified in the this bracket. Okay, I think you got this point. So here you are not calculating the number of cells here based on the given delta x, that is the minimum size of the cells in that direction, which is specified here, that is delta x, delta y, and delta z. And based on this delta value, it is going to calculate the number of cells. So x cells is calculated here, x, y cells, and z cells. Okay, this approach is I prefer this kind of approach, because this way you can fix the delta size in x, y, and z direction. So if you are fixing the number of cells in that scenario, if the means the length in that direction is not equivalent. What I mean to say, suppose in the x direction you have 1 meter. In y direction, suppose your dimension is 2 meter, and in z direction, suppose dimension is 3 meter. And if you are keeping the number of cells as a fixed quantity, then here it is going to be the cell size would be different in the x direction, cell size would be different in the y direction, and cell size would be different in z direction. So that is why I prefer this approach, that I always fix the cell size, delta size in given direction. Okay, so this way you can fix the delta value, and the numbers of cells will be calculated automatically by using such kind of expressions. Okay, now whatever the x min, x man, or different values you have defined, you are using to create the block here. That thing I have Abhishek has already uh, means told yesterday class. So this is the such similar this thing, only here that whatever the values you are giving as a numerical value, here you are giving as a variable. Okay, now this x cells already we have calculated, and here we are currently using the simple grading. So there is no going to be any multi-grading kind of things in this simple grading approach. Okay, this is already explained by Abhishek. This is the boundary that you have already know. Okay, so this way you can use the dynamic kind of meshing, and this is useful if you are doing the parametric study. So in that way you have to just only change the this means x min, x man, max, y min, y max, and z min, z max. This value you have to only change based on your requirements. Other things you can keep the constant if you are doing the parametric study. Okay, so I'm not running this, and I'm not going to show. Now this is important, that is the multi-grading. So I've taken same examples for the multi-grading. Okay, so here we have fixed the number of cells. Okay, as I told you that this approach you can also utilize for your machine. So I've taken 40 cells in x direction, y direction I have taken 40 cells just for the demonstration purpose. Okay, so you can see that how cells has been divided. Okay, now this is the way of the doing the multi-grading. Okay, as I told you that on this slide, either you can use this approach. Okay, you can create 4 different blocks, and you can do the grading from wall to the center, and this 4 blocks you can connect as a single block. Okay, this one way technique. Other technique is that you can use this simple grading means this expansion ratio, this whatever the parameters that you are going to specify, this is a given for the x direction, this is the given for the y direction, and this is given for the z direction. Okay, so since in z direction I am keeping only one cell, so that is why I have given no expansion ratio, just I am giving the value equal to 1. But in other direction, like in the x direction, we want to give the simple expression. Okay, so here this first value that you are going to specify, that is going to give you the number of cells, how many percentage you are distributing. Okay, so for example, if suppose if you want to keep 100 cells in x direction, for example, suppose you want to give 100 cells in x direction. So it means that I want to divide that x length into 3 portions. That is the 0.2 value, 0.6 value, and 0.2 value. Okay, means 20% cells, 60% cells, and 20% cells. Okay, so here it means that 20 cells will be this 3 portion of the x direction will be divided into 3 equal parts, and 20% cells is going to be distributed into the one part, 60% cells is going to be distributed in the middle part, and 20% cells is going to be distributed in the uh, no, sorry, I'm mistake here. This is this first code is for the length division. Okay, so suppose we have 1 mm length, sorry, 1 meter. So the first interpretation, that is 0.2, 0.6, and 0.2. So it is going to be 0.2 length, then 0.6, and then 0.2. Okay, so this 1 meter has been divided into 3 parts. That is the 0.2 meter, 0.6 meter, and 0.2 meter. Now, as I told you that I want that 100 cells. So I want that there should be 100 cells given in x direction. So now this 100 cells is going to be distributed on these 3 portions. Okay, so this 100% cells, that is the 25% cells, is going to be given for this 0.2. 50% is cells is going to be given into the this 0.6 mm length, and this 25% length is going to be the given this 0.2 meter length. Okay, so this is where, so 25% means 25 cells, then 50 cells, and then 25 cells. Okay, so you can just sum up this. This should be going to be the if you are talking about in the terms of the percentage, this should be equal to the 100, and if you are adding these terms, this should be equal to 1. So 0.25 plus 0.5 plus 0.25, this should be equal to 1. So this second term should be always equal to either 100% or equal to 1. Okay, now this last term, that is for the expansion. Okay, so as I told you that uh, this is the expansion ratio. So this expansion ratio is going to work only for this given length. So for 0.2 mm, I want that expansion ratio equal to 8. Expansion ratio equal to 8 means that this 0.2 has the wall length equal to, that is let me open this slide. So that is equal to del E, that is the end cell upon the starting cell, equal to 8. Okay, so near the wall, the means the cell should be, the length of cell should be divided in such that the length near the wall, and if you are dividing the cell at the middle of the wall, sorry, middle of the this 0.2 mm length, then the ratio equal to 8. Now in the center of this x length, we are keeping the cell size equal to 1. So we are not giving the grading system into the middle of this middle portion of this given length. And for the this ratio equal to 1 by 8. So now this means del E, that is the delta E, that is delta is now on the right side. So now right side upon the middle, that is the delta S, when we are going to divide, that is going to be equal to the 1 by 8. Okay, so in this way we can distribute the simple grading in the x direction, and similarly this approach is followed in the y direction. So now let me run the blockMesh for this example. 6 can let me zoom in a little bit. Okay, sorry, there is a version issue. So actually we are getting error because when you open the OpenFOAM 6 file, any of the OpenFOAM 6 file, any examples, So then you are going to see this thing, that is version 2.0 is written there. So this has been removed in the later version of the OpenFOAM. So that is why we are seeing the error. And we are going to we need to add in every folder. Okay, so now the blockMesh is run, but I think we are still going to get the error. Okay, because in these folders constant we have not added it, and still we are going to get error with us. Sorry, this zero is not going to be read by the OpenFOAM. Okay, so now we are able to open the meshings, and you can see here that this is x direction and this is the y direction. Okay, so if you take the x direction, okay, so in this case you can see here that the if you divide the means from till here, that is till this point, from this point to this point, the cell size are completely uniform. Okay, but from this point to this point, okay, the cell size are distributed in a non-uniform manner. And if you let zoom it, so you can see here that this, maybe I can show you the scaling. Okay, so here scaling you can see, I'm not able to show the sizes here. Okay, so maybe you have some idea that this is the this cell size is the much larger compared to this starting cell size, and you can say that this is around 8 times to the this cell size. This is the first one. Similarly, you can relate in this end, that is the x end, and similarly you can relate in the y positive and y negative direction. Okay, so this way you can use the simple grading. This type of technique is required while you are going to solve the turbulent models. Okay, so where this wall, if y plus distance is important factor, in that scenario this y plus this multi-block grading is required. Okay, now this is the end from the my side for the block mesh. Now you can go to the that FPOM and simpleFoam and pimpleFoam algorithm. Okay, so you have any kind of question, then you can ask in the chat box, and uh, mentors will be help you out. So first, let's understand the what are the governing equations we are going to solve, and how this OpenFOAM handles the finite volume method. Okay. So speaking of the governing equations, generally this open means fluid mechanics. We solve the conservation of mass and momentum. Okay, for a given fluid flow, and the assumption is that fluid is regarded as the continuum. Okay, and while solving the problems, we assume that flow is described as the macroscopic properties. So the difference between the microscopic and macroscopic, that uh, while you are going to deal with the each and every component of a given particles, then it is known as the microscopic. But if we take as a control value, then we consider as a macroscopic properties. So while solving the fluid flow problem, we 1 minute. So while solving the fluid flow problem, we assume that we are dealing with the microscopic properties. So whatever the physical properties we take for the fluid, like density, viscosity, we don't take at a given particle location. We consider it as a bulk system, and we take that properties for solving the fluid flow. Okay. In general, speaking about the mass and momentum conservations, we general follow the three fundamental physics law, that is the mass and energy conservation. So this one we can say that mass conservation, second we can say the energy conservation, and the third one that we follow, that is the Newton's second law, that is the F equal to ma. Okay, so these three general physical law we follow to derive the means Navier-Stokes equation and the continuity equations. Okay, so this is the general equations for the mass conservation for a compressible flow. So this is the general equations in a given Cartesian coordinates. Okay, now we can relate from this given equation, that is the conservation equation. So this first term is known as the transient term, and if we use the del operator here, then we can write these three terms as a this there's the del dot rho into u, and this is known as the convective term. Okay, so this transient term and convective term, you can whatever the any kind of the scalar equations, scalar partial differential equation, either for the mass transfer or the species transfer that you are going to write, you need to have this transient term as well as this convective term. So this is the general form for the density. Similarly, you can write this kind of equation for any kind of the phi scalar properties. So this density can any physical properties, that is the phi. Okay, now where the problem occurs, that if you want to write the Navier-Stokes equations and the this continuity equations, so we can write four equations. If you write the each and every component of this velocity, so this is the for the x direction, this is for the y direction, this is for the z directions, and this is the one continuity equations. So the problem here, that if we see these four equations, then we have a five unknowns, three velocity components, one pressure one pressure value, and this one is that is a density. So we have five unknowns, but we have only four equations. Okay. Okay. So and if you want to solve for the density, then we can use the equation of state. Okay, that we can use to find out this means this property that is a density. But still we have now we have a total 4 equation, and we have 4 governing equation, but there is still a problem that we are going to see. So if you see the equations, this terms is known as the inertial force, this is the pressure force, this is the viscous force, and this is the external force, any kind of external force that can be, we can assume here. Okay, so the problem here is that one is that is a non-linearity present in this equation. So this equations and this term is known as the non-linearity in the given partial differential equations. So this non-linearity we have to deal with, and also there is a, we don't have any explicit equation for the pressure here. Okay, so if we write these 3 equations, then this equation can, we can say that there is, this is the explicit equation for the u component of the velocity, this is for the v component of the velocity, and this is for the z component of the velocity. But we don't have any explicit equation for the pressure that we can say. These two problems we have to tackle out to solve the non-linearity. So we cannot expect the exact solution, but we can use the iterative method, and in generally to solve the flow problem or the Navier-Stokes equation in simpleFoam or pimpleFoam algorithm, we use the Picard kind of the iterative method. So what is the Picard kind of iterative method? So when we take the value from the previous solution, and we use those previous solution to find out the current time step solution, this kind of the iterative method is known as the Picard kind of iterative method. Okay, so we can solve this non-related linearity problem, but still we have a that we don't have any pressure equations for the pressures. Okay, so for that purpose we can use the pressure we can use the pressure velocity coupling. So let's see first that what are the different meshes criteria is being used to solve the Navier-Stokes equation. So if we speak about the finite element method, so let me give you one 1D example. So this is, suppose we have 1D geometry, and it is being discretized in the different cells. So this is the cell center that marked in the yellow. This is the waste cell. Okay, this is the WW cells. You can say that that is the one cell ahead of this W cells, and this is the east cell, and this is the double E cells. Okay, so this we can assume as the delta XC and delta WE. Okay, so in staggered method, okay, we use that pressure and other scalar quantities are given at the cell center, but the whatever the momentum equations that we are going to solve, that is the means velocity component that we assigned on the phase center. So this kind of approach is generally used in the finite element method, and this is known as the staggered meshing. Okay, so when you take the means pressure and other scalar quantity as the cell center, but a vector quantity, that is, you can say that the component W, V, and Z at the phase center. So in such meshing is known as the staggered meshing. Okay, but in OpenFOAM we don't use the staggered meshing because we take all the field variable at the cell center. Okay, now let's see that what problem we are going to face if we take any cell center. If we take all the field variables at the cell center, then what problems we are going to face. Okay, generally in OpenFOAM or any kind of the software that follows the OpenFOAM, generally we use the two kind of the discretization. Okay, so one is upwind kind of discretization, and second one is the central difference method. Okay, so this central difference, taking the example of the central difference method and this that 1D cells that I'm showing here, if we're giving every scalar field variable at a cell center and also vector field variable at the cell center, then it is known as the collocated meshing. Okay, so means I think you have now idea about what is the staggered kind of meshing and what is the collocated kind of meshing. So in OpenFOAM, as you see that whatever the field variables you create in the create field.h, then only we specify for the given. Yes, we will upload the slides, don't worry. So whatever the field variables we are defining at the sense centers. So if you open the create field that you can see that we are all, when as long as we are defining any volume vector field or any scalar field, we are going to assign in a given cell center. Okay. So let me first discretize this equation, that is the momentum equations. So I am just ignoring the body forces. Just I want to show that what problem we are going to face if we going to discretize the momentum equation at a 1D cells, assuming that all the field variables are assigned in the cell center. Okay, so this way you can use the divergence theorem, and you can discretize in this way. So this is the this term m dot t into ue, m dot w into uw. This is the second term, and this is the pressure term. Okay. Now, means first let's focus on the this pressure gradient term for a given this 1D cells. Okay. So this first term that you can write me dot e plus m dot w equal to 0, but while we are going to discretize for the pressure term, so this is the pressure gradient I am taking just for the x directions. Okay. So this pressure terms that we can discretize using the central differentiation. So we can write as the Pe minus Pw upon 2 del x. Okay, so if you are taking this as a cell center and assume that we are assuming that uniform cell grading. Okay, so this del x w equal to del xc equal to, we can assume that del x. Okay, so if you use the uh, means we can use the central difference, then this is the this del p upon del x into dv can be written as the Pe minus Pw upon 2 del x plus Vc. So one problem you can see at this level, that while we are calculating the pressure gradient, we are not taking consideration of this cell center value. Okay, so we are calculating the pressure gradient at the cell center, but while we are using the central difference approach, we are not taking consideration of the pressure value at this cell center. This is one problem if we are using the collocated grid kind of meshing. Okay, so this is the one problem. And second problem is that since we are not means suppose the value at the value of the pressure is this value, this cell and this cell is minus 50 and plus 50. Okay, so now while we are going to calculate the del p upon del x, then this value is going to be equal to 0. Okay, so so we are not finding any pressure gradient, because this, while we are calculating del p upon del x, this value is automatically becoming the 0. So in this scenario, this problem is known as the zigzag kind of problem. Okay, which is the kind of the non-physical situations. So that is why this I have just shown example for the momentum equation, but this same is true for the continuity equations also. Okay, so the two problems that I can means I want to focus here, that while you are using the collocated grid kind of meshing, while we are calculating the pressure gradient at a center cell, so we are taking the value from the alternative grid points. We are not taking consideration for the cell center, and since we are calculating from the alternative grid points, so we are going to get a non-physical kind of the zigzag pressure value and the velocity field also. So I have just shown example for the pressure field. Similarly, if you want to calculate, you can get the this value is also going to be the face the zigzag kind of the problem. Okay, so this is the problem that we need to tackle out. Okay, so these things I have means I have already told in the last slide. These are the just calculation. Okay, so this discretization also shows for the momentum equation that we are not taking consideration of the cell center value for the momentum while calculating the while we are discretizing the Navier-Stokes equation using the central differentiation method. Okay, so means I think you have now understand the problem that we have first we have means we need to use the iterative method because we have a like non-linearity in the momentum equation. Second, while we are using the this collocated grid meshing, then this collocated mesh grading has two problem. That is the we are creating the zigzag type of solution, and second, we are not considering the values for the cell center while calculating the pressure gradient or the other physical other velocity scalar quantities. It's either vector or scalar quantities. Okay, so I think now this problem, let me first explain that what kind of solution is provided in OpenFOAM by taking a simple example. Then we will I am also going to show you the derivation also. Okay, first let's understand the solution in the form of the matrix, then I am going to show you the derivation also. Okay, so this is the continuity equation and this is the momentum equations. Okay, so if you want to write these two equation in the matrix form, then we can write as this form. Okay, so you can see here that if you multiply these two terms, okay, this terms and this term are equal to E of V, that is the body force or any other force, then you can write the this uh, momentum equations. Okay, so this different terms, if you linear if you discretize this different terms, if you form a matrix, then F is one matrix, B transpose of B is another matrix, and if you multiply these two terms with the U and P, where U and V and P are the unknowns, then we are going to get a this second equation, that is the momentum equation. And if you write this equation, that is B into 0, and you are going to multiply with the V and P equal to 0, then you are going to get the this equation, that is the continuity equations. Okay, so this just we want to write this two equation in the form of the matrices. Okay, now as you can see here that this is the 0, so this is known as the saddle point. Okay, so if you have read the means the linear algebra, so you may know that this, if there is a 0, then the rank of this matrix is going to be the lesser than the rank of the augmented matrix, and this can cause the saddle point, means that we are not going to find any exact solution. Okay, so that is why we need to find out the iterative solution. Okay, and at the same time we need to find out a equation for the pressure. Okay, so what is the approach here? So we can decompose this A matrix, that is the F bt into B into 0, into the means the lower matrix and the upper triangular matrix. So this is the lower triangular matrix and this is the upper triangular matrix. Okay, this kind of approach is used to means this discover complement matrix is generally used to linear decompose any matrix into the form of the lower and upper triangular matrix. So this matrix is you might have heard in the while learning the algebra linear algebra. So this matrix, that is the F inverse, is known as the so sorry, this complete matrix is known as the complement matrix. Okay, now we can put this lower triangular matrix and upper triangular matrix into these equations. So instead of A, we can put this complete two matrix in the form of the lower and upper triangular matrix. Okay, so this is what I'm saying, that this is the complete A, then this B and P, and this is equal to the body force and 0. Okay, now this that is the first that is the upper triangular matrix, and V into P can be written as the V star into the P star. Okay, so means that you can see that while you are going to solve this two matrix, that is the this upper triangle matrix and V and P, then you are going to get a V star and P star. Okay, now using this V and P star, then we are going to solve this equations, this complete equations, and here we are going to means this, for simplicity purpose we are taking the this F inverse, and the that is the inverse of a diagonal matrix. Okay, so first we are getting the V star and P star, then using this V star and P star we are solving this complete matrix. Okay, using this body forces. Okay, so this is approach that we can summarize into the 4 steps like this. Okay, so this is the what we are going to start with. First, taking the initial boundary condition in this complete matrix here, and using the we are going to first solve for the V star. Okay, so this you can see here that this term, that is F into 0, and this V star is going to give you this FV. First we are solving for this F into V star equal to the FV, that is the body force. So from here we are going to get the predicted this velocity, that is the V star. Okay, now from this, using this V star value, we are going to calculate the P star. So this second term that we are going to multiply here, and since here this side equal to 0, so you can write this term equal to the minus B into V star. Okay, so here we are going to calculate the P star value. Okay, now this P star has been calculated using the V star value. So this V star is actually satisfying the momentum equation but not the continuity equations. Okay, so for that purpose now we are going to use this first term of this given matrix. Okay, so this equation that we are going to utilize, and from here we are going to update the value of V. Okay, so here we are updating the value, taking the value of the P star from the last iterations. Okay, so this is again, this iteration will continue until and unless we are not going to get the convergence solution. Okay, this is just simplified for the using the matrix form. Now we are going to see the derivation of the given equations. Okay, this whatever I told you, these steps that we it has been just given in the different slides. You may visit the slides later. Now let's see the derivation, actual derivation. Okay, this was just a simplification in the forms of the matrix. Now we can see the actual derivation for the pressure velocity coupling. Okay, so in the actual scenario, while we are going to solve the continuity equation and the momentum equations, we generally take the divergence of the momentum equation to find out the divergence free velocity condition, and that is going to be act as the one equation for the pressure, and that is going to be act as the pressure character term. Okay, so this is the whole idea about the finding the different equations for the pressure in terms of the velocity, and let me show you the derivation, then you have a better idea. Okay, so this is the two equations. This, if you want, I want to discretize this term, that is the continuity equations. So let's take that we find a velocity, that is the V star, at a intermediate terms. Okay, so from using the initial pressure value condition and initial velocity conditions, we solve these equations, and suppose we are solving for the V star, that is the intermediate terms for the velocity. Okay, now we find, using this equation we find the V star. Okay, so it satisfied the momentum equation but does not satisfy the continuity equations. Okay, now since it is not satisfying the continuity equations, so there might be some error in this value, that is in the V star. Okay, suppose if we are adding the, that is the V dash value, that is the correction terms in this V star, that this Vn plus 1 is going to satisfy the continuity as well as the momentum equations. Okay, so I mean to say that we've solved the momentum equation using the initial pressure value and the velocity value, and we find some solution, that is the V star. Now this V star is satisfying the momentum equation but does not satisfying the continuity equations. Okay, so that is why we need a corrector. So we want to correct this V star value, and suppose this corrector term is the V dash. Okay, so if we add this V dash into the V star, then this is going to give one value, that is Vn plus 1. And similarly, there is going to be a one correction term in the pressure value, pressure field, and that is the P dash, and this is going to be the Pn plus 1. Okay, so Pn plus 1 and Vn plus 1 is the final solution. And now we can put this solution, that is the Vn plus 1 and Pn plus 1, into the final momentum equation and the pressure equation, continuity equations. Okay, so V star is the solution at the intermediate level, which is not satisfying the continuity equations, but and the this Vn plus 1 is the final solution, assuming that this V dash is the velocity character and P dash is the pressure character. Okay, so as I told you that means if this is the equation number 2 and this is the equation number 1. Okay, now if we subtract this two equation, that equation 2 minus the equation 1, okay, and if we put this whatever the value we are finding here for the Vn plus 1 and Pn plus 1, then we are going to get the relation between the pressure character and the velocity character. Okay, let me again repeat what I mean to say that. So this is the equations for the V star and this is the equations for the Vn plus 1. Okay, and we have Vn plus 1 equal to V star plus V dash, Pn plus 1 equal to the Pn plus P dash. Okay, so if we subtract equation 2 and equation 1, so equation 2 minus equation 1, and if we put this Vn plus equal to V star plus V dash, Pn plus 1 equal to the Pn plus P dash, then we are going to get a this term, that is the V dash equal to the minus delta P upon rho equal to the delta P dash. That is the correlation between the pressure character term and into the velocity character term. Okay, so if anyone has any question till now, I think today is the much means very boring class because only theory is there. Yes, the zigzag problem is also known as the checkerboard problem. So in two means while taking example in the 2D 2D meshing, that is known as the checkerboard problem. Jamshed, I did not understand the question. Can particle based method? I think OpenFOAM only works for the means finite volume method. There is no anything like particle method. But I think some of the solvers in nowadays using this SPH kind of the method using the finite volume, means by taking continuum assumptions for the SPH kind of the problem. Now this some of the Lagrangian or SPH kind of the method has been applied in the OpenFOAM in the latest version of solver. I'm not sure about the OpenFOAM 6. Okay. PV method using flowchart means PV. Yeah, I will explain. Let me go to the this simpleFoam algorithm, then I will explain. I'm just showing you the derivation till now. Yes. So let me give me some break. So I think till here everything is clear. We have get a one separate equation for the pressure. Means we have get a correlation between the pressure character and the velocity character. So this is what I mean to say, that we are subtracting equation 2 minus equation 1, and that is where we are getting this v dash equal to the minus delta upon rho equal to the minus del p dash. Okay. So now if we take the divergence of this v dash uh, minus delta upon rho upon del p into the p dash, and if we use this correlation, okay, then we will get the Poisson's equation of the pressure correction. Okay. So means what happens that this delta p is now it becomes the Laplacian term, and this v dash become the delta into the v star. Okay. So that is the equations for the Poisson's equation of the pressure correction, and that we are going to solve for the pressure corrector. That is the pressure corrector method that we are going to use for in the simple algorithm or the pressure algorithm. Okay. So what are the different that derivation that I've told? So for a simple scheme, if I want to summarize, I can summarize like that. Okay. So we are starting with the momentum equations by taking the every examples or everything the values from the last iteration, and using those value from the last iteration we are solving the momentum equation, and in that step we are getting the v star value. Okay. So the resulting velocity converts the momentum but not the mass. Okay. So that is why we are going to use the constructed velocity corrector step to find out the corrected pressure, and using the pressure corrector step we are finding out the corrected velocity, and again then we will go to the this first step, that is to solve the momentum equation. Means using the last step the pressure value, and then again this step will continue from 3 to 1, 312 312 until we are not going to get the convergence value. Okay. So this is this steps I want to show from the perspective of the OpenFOAM. So in terms of the this different cell values, suppose I am solving for a cell value that is the P. So this is the equation for the AP and UP for the current cell value, and this is the value for the neighboring cell value, and this is the body force, and this is the pressure field. Okay. So this is the momentum equation that has been discretized on a given cell domain. Okay. So this is the value for the current cell, this is for the neighboring cell, this is the body force, and this is the pressure field. Okay. and this step that is known as the pressure corrector step. Okay, so this row APU to the inverse into the delta P, and this equal to the rho into APU into the minus H into HU. Okay, now this APU in OpenFOAM is known as the denoted as the UE equation dot A into the bracket. Okay, and this HU is known as the UE equation dot H. Okay, so what is this HU is the FV minus this complete neighboring cells value. Okay, I think I have included one slide. Okay, so I have one slide here I forgot to add. So this HU value is the FV minus this neighboring cell value, that is the AN into the UN. So this is the HU, and this APU is equal to UE dot A. So these two terms, that is UE equation dot A and UE equation dot H in OpenFOAM, it is specifically defined to make the algorithm simpler. Okay, so this two term is generally used in the OpenFOAM only. In other software, in other CFD software, these two terms is not being used as shown on the figure, on shown on the slide. Okay, now after solving this pressure corrector terms, okay, using this corrected pressure, we are modifying the UP here. Okay, so we are updating the U here using these equations. Okay, so means there's two terms that I'm saying here, that we are updating the U and we are updating the P, and then again we are going to the step 1, then step 2, then again up step 3. Step 3 includes this updating the U and P. I have written separately. So this iterative approach is followed until and unless we are not going to get the solution. Okay, so this is the algorithm that you can see in the OpenFOAM. Okay, so we start from the U equations, we solve U equation minus delta P, then we solve for the this pressure character value, and using this delta P we are going to get the update the velocity, and then we go to the start step. Okay, so this iteration is followed until and unless we are not going to get the solution. Okay, and the code that you can see are on the left side. So this is the code that is the U equations. Okay, and here you solve for the minus delta P, U equation minus delta P, and this is the pressure corrector step. Okay, and this is where you are going to update the velocity based on the pressure value. This here you are finding the pressure value, corrected pressure, and using this corrected pressure you are finding the U here, and then this again U is going to act as a this boundary condition in the U equation here, and then this iteration will be followed. Here again this HU that I have said that this HU equal to the R minus AN into this neighboring cell value. So R can be any forces, any body force or any kind of the source term that you are specifying here, that can be given in the R term. Okay, so this is the algorithm for the simple. There is a slightly difference between the PISO algorithm. Okay, so first difference is that simple algorithm solve for the steady state solution, and PISO algorithm we solve for the transient term also. Okay, so you can see here that see we are going to cover only the incompressible flow for now, but there is a separate session for the compressible flow. Okay, but in the later version of the session. And Anirban, I did not get your question. What is U and U in the step 2? Which slide you are talking about? Which slide you are talking about? Here. This slide. So this UP is this, sorry, this you are asking what this. So I said that this terms we are updating pressure here, we are updating the velocity here. This just I have written separately, but this is the same step. Yes, we are going to cover, don't worry. Okay. So this update, you update P I have written separately, but this is the same step, step 2 and step 3. That here we are updating the pressure, we are updating the velocity. This is the same thing I have written here. Okay. So this is the PISO algorithm. Okay. So PISO algorithm is for the transient term also. So you can see here that in the UE equation we have dtu. Okay. But in simple there is no. Sorry, simple is also written here. So this is a mistake from my side. In simple, we solve for the only steady state. Okay. So this here the UE equation we solve, and another difference is that, so instead of going directly from the top step, we just correct this pressure corrector, and velocity corrector step. We take another iteration here. So instead of going from step 1, 2, 3, then 3, 1, 2, we just uh, take one or two iteration in among the between the step 2 and 3. Okay, what I mean to say that we solve for these equations. Okay, then using that values we solve the pressure corrector, and then we find the velocity corrector step. So instead of going from step 3 to step 1, we just go to the step 2. Okay, in the PISO form. Okay, so we take this UP value, and using this UP value we again correct the pressure value, and from again correcting the pressure value we find the UP value, and then again we go to the step 1. Okay, so this is instead of only one correction term, we have one another inner corrector step. So that is difference between the simple and PISO form. So here you can see here that in simple there is only one character. So from start time to it is going to end time, and then it is going to the start time. But in PISO form there is another character that from here start time it is going to solve, and then before going to the first time step it is going to the again solve the pressure character step. So this step is going to again solve, then again it will update the u, and then it will go to the start time. So that is difference between the simple form and the PISO form. Okay. Now this non-orthogonal character that you are seeing here on this slide and this slide, this is something related that when you have mesh which has the non-orthogonal issue, the problem is of the non-orthogonal is there in the meshing. So then this non-orthogonal character is required here. So that is not something related to the algorithm of the PISO or simple form. So this is something related to the orthogonality issue. Okay. So as Abhishek told in the study class that orthogonality quality should be checked while doing the meshing of the given domain or given geometry. So if mesh has the non-orthogonality issue, then this character should be specified here. Okay. So you can see that here only one iteration is there, and here there is another iteration is there. Okay. So PISO is solving we for the transient solution, steady state simple form we solve for the steady state solution. Now combining the simple and PISO, we have another solution known as the PIMPLE form, PIMPLE algorithm. Okay. So let me show you the solver here. So this solver I have copied in this folder. Okay, so first let me show you the simpleFoam.c. Okay. So if I open the create fields.h, so you can see here that we are creating this volume scalar field for each mesh here. Similarly, we are creating the volume vector field for the each mesh here. Okay. So it means that we are creating these values at the central cell center. Mesh is one object. Okay. For each mesh object, we are creating the value of vector field that is the P. Okay, and if you go to this, go and see the definition of this volume scalar field and here volume vector field, you are going to see that this values, this field values are going to be defined at the cell center of a given cell. Okay, that is what I told you, that in OpenFOAM collocated grid meshing is being followed. Okay, now if you open the simpleFoam.c, so here you can see that this is the steady state solver for the incompressible turbulent flow using the simple algorithm. Okay, now here you can see that there is no any outer character is followed while solving the PE and UE equations. Okay, but when you open the PISO form, you can see here that there is one PISO character that is going to be solved for the pressure character loop. Okay, so before going to the iteration one, that is the that first outer character, it is going to have a one inner character that is known as the pressure velocity PISO character. Okay, so it is going to iterate for another time, or whatever the character iteration you are providing in the FV solution folder, that is going to iterate for that number of time to solve the pressure character term, and then it is going to be solved for the outer character term. Okay, and if you see the UE equations in both the cases, like PISO and the simpleFoam. So in PISO there is a transient term is included, but in simpleFoam you are not having this transient term. Okay, so this is the divergence of phi u. Okay, let me show you the equations. Okay, so this is the transient term, this is the convective term, and then other terms are given here. So this is for the, if your mesh has some moving part, then this mrf dot ddtu is term is included. This is for the turbulence term. Okay, so if you are using the turbulence term, then this is going to be solved. And this is for if you have any other force term. If any other body force is given here, then you can use the FV option utility of the OpenFOAM. Okay, now here you can see here that this is going to create one matrix. Okay, that is the in since you are going to you are using the FVM, so this is going to give away one matrix in terms of the unknown u. Okay, now here we are going to solve using the pressure gradient. Okay, so this is this, other than this pressure gradient, this is going to give this is going to include the all the terms of this Navier-Stokes equations except the pressure terms. And why it is done here? Because we need to calculate the UV equation dot A and UV equation dot H, that I have told you that it is the specific quality of the OpenFOAM. Sorry, let me open the P equation. So that is because UV equation is, we are going to calculate the this A operator and dot H operator. That is why it is being solved separately. The gradient term of the pressure is solved with the U equation separately, because this U equation we are going to calculate the dot A term and dot H term. Okay, so that is why this is being solved separately. Okay, now here you can see that this again a few option is correct, and if you want to specify the relaxation factor, then here you can write the U equation dot relax. Okay, now this RAU term is calculated, H by A term is calculated, and this, since this is the volume vector field, we need to calculate the surface scalar field of this term, that is the H by A. So this, using this this flux term, that is the FVC dot semicolon flux equal to H by A, is going to give you a surface scalar field. Now this is something related to the MRF, that is the moving mesh zone is given in the given in your problem, then this is related to that thing. Okay, here we are going to solve the pressure character term. Okay, so this H using the phi H by A and RAU, we are going to solve the P equation. Okay, that is the pressure character term, and that is where this pressure PISO, this is something related to the north orthogonality. Okay, so if I show you slide, so this is what I said, that it is going to solve for the non-orthogonal. So if your mesh has some non-orthogonality issue, then this is going to be iterate here. Okay, can you maybe slow the implementation file? So I am opening this PISO solver. So here this U equation.h and P equation.h is given here. Okay, and this PISO form is the source file. Okay, so loop is starting from here and ending here. So first it is going to solve for the U equations, then it is going to solve for the P equations, and that is difference between the PISO and the simple form, because in PISO we iterate for the pressure character term more than one time, but in simple, if you open the simple form, we don't iterate for the more than one time. Okay, so in simple form you can see that we are directly written these two equations. Okay, and this is the pressure character terms. Okay, now this phi term, that is the phi is the what is the phi, let me tell you. So as I told you that this momentum equation has non-linearity while solving this term. Okay, so this terms you can see here that there is a two component of the velocity. Okay, so this non-linearity has been avoided in OpenFOAM using this phi term. Okay, so this phi is nothing but velocity from the last term. Okay, so the velocity of the last iteration is known as the phi here, and you can see here that that is similar to this term here, the divergence of u into u. So here u, this u is taking for the current iteration, and this phi is the u, that is the velocity from the last iteration. Okay, and that is updated here only. Okay, so that is updated after after finding the correct value of the velocity, and this phi is being stored as the phi, and while you are going to take this iteration for the u equations, this phi is going to be uh, take the numerical value of the velocity is taken here, but another u is taken as the means unknown value. Okay, so this is how this non-linearity has been avoided in the OpenFOAM. Okay, so this pressure character is going to be solved, and from solving this pressure character we have a one corrected pressure, and using this corrected pressures we are going to find out the this u, that is the velocity for the this iteration we are going to use this corrected pressure to find out the u value, that is the velocity value. And using this u value, the values boundary condition has been corrected. So the values that you have find that you have given in the zero folder of the initial boundary condition, those values need to be updated at after every iteration. So that is there, this correct boundary condition function is going to be update the value of the velocity field here. Okay, and after solving this equation, again it is going to iterate for the u, and then it is going to solve this u equation minus gradient of the pressure. Then again it is going to be the pressure character step, and then again it is going to calculate the phi, and then after that it is going to calculate the u equations, means corrected velocity, and then it is going to correct the boundary condition. So this is how this iteration works for the PISO form. So there is slightly difference between the simple form and PISO form. I think you have now a clear idea about that what is the difference between the PISO and simple form. Okay, now let me open the pimple form. So at this level, means if you are still have some confusion about the simple form or PISO form, we are going to do one session on coding the simple form from the zero level. Okay, so we will start with the form new year, and we are going to code our every term of the simple algorithm. So one side we have a simple algorithm, written there, and another side we are going to code the each and every term of the simple form. So in that point, your in every concept of the algorithm is going to be clear. Okay, so don't worry if you have still confusion about anything about the simple form or the PISO form at this level. Okay, so pimple form is a version of combination of the simple form and the PISO form. Okay, the only difference is that PISO in so here is the pimple character is given, that is similar to the PISO form. Okay, now this outer character is of course given in the simple form, but in pimple form is the solver for the steady state solver. Okay, so that is the benefit of the both simple and the pimple PISO form is given in the pimple form. Okay, so that is the only difference between the PISO and the pimple form. Okay, so if we see the test cases, then you can see that how this test cases is different for the different algorithm. Okay, so if you open the simple form and if you go to the FB solution folder, okay, so you can see here that there is no any outer character is given for the simple form. Okay, here only character is given for the orthogonality. If your mesh has some issue related to the orthogonal, then you are going to give here some values. Okay, since here this example is a PITS jelly example and it is using the utility of the blockMeshDict, so the mesh is going to be hexahedral, so there is no going to be issue of the orthogonality issue. That is why there is no requirement of the given this value, this non-orthogonal, this character is given, that is the 0. Okay, because each cell has the hexahedral mesh, so there is no any correction is required. But if you are getting mesh from the some other software, then your mesh might have some problem, a non-orthogonal problem. In that scenario, you are going to give some value. So generally this value should be means around 2. So if you are facing issue while solving some problem, if you are facing some uh, issue related to the meshing, try to modify this term also. Try to put this value like 2. Sometimes it works for the 10 also. What is the source term in the pressure equation? So this equations, this gradient p is act as a source term in the equations. Okay, so that is why you can see here that this we are taking as the FVC. So I told you the difference between the FVM and the FVC, finite volume method and finite volume control method. So this is the here we are taking as a FVC because we are treating as a source term into the U equation dot h, whatever the matrix we have formed here. Okay, so this FVC gradient is acting as the source term here. Okay, so this non-orthogonal is something related to the mesh issue. But if you open the file for the PISO form, see if I open the file for the PISO form, and then you can see here that there another term that is specified as n characters equal to 2. Okay, so that is where this PISO form, this PISO character is being asked here. So it is going to solve this pressure coupling, pressure velocity coupling for the 2 times. That is what is this means here. So here also you can see that there is a non-orthogonal character that is equal to the 0. So here also there is no requirement of the any correction because here also we are using the blockMesh method. BlockMeshDict, as long as you are using the BlockMeshDict, you will have a going to have a means good quality mesh, and there is no any issue related to the orthogonality. Okay, so this n character is related to something related to the PISO character that I am showing here. Okay, so this is something related to the this character. Now if you go to the pimple form, any test case in the pimple form, so there is another terms that you are going to find out. There is another variables that is the n outer character. Okay, so in pimple form, this Okay, so this pimple loop is going to be solved. How much times of you are specifying in the every solution. So if you are specifying for the 2 times, so for the current time step, since it is a transient solver, so that is why this an outer character is given here. In simpleFoam, time step is not important, but in pimpleFoam, time step is important. Okay, so for the given time state, it is going to solve this complete governing equation for the 2 times. Okay, so that is why this outer character is given in the pimpleFoam. Okay, because it is a transient solver, so every time step is important, and every time step it is going to solve this all the governing equations. And here this pimple dot correct is given for the pressure velocity coupling here. Okay, so in that is why pimpleFoam is a combination of the PISO plus simpleFoam. Okay, that is, you can see here that in the every solution. Okay, again here you can specify the non-orthogonal, and this again onion character is something related to the PISO. Okay, so now I think you have now some idea about the how this different algorithm. Now you can, at least you can, at this level you can just go through the solvers and you can see that what are the different terms are means what are the different terms are doing here. Okay, so this pimple, PISO and simpleFoam, this algorithm is generally followed in the means it is the base of the solvers. In any kind of the solvers that you are going to see in the OpenFOAM, these are the base of the solvers. Some modification, for in example of the compressible flow density, the variation of the density is important. So some variation you might get, but this is the base, that is the algorithm, that is the steps that you are seeing here. This is the base for the any solver. Okay, so that is how P equation is solved, how pressure coupling is done, and how this means how iteration is being done between the pressure and velocity term. So this is going to be the base of the every solver. Okay, you are asking about the H by M. Sorry. See, if I show you the equations, so these equations we are solving here. Okay, so this U equation 1 by A in multiply by HU is known as the RHU, H by A. Okay, so this RAU is calculated here 1 by U equation dot A, and when you are multiplying with the U equation dot H, then H by A is calculated here. Okay, now since we are calculating the divergence here, so that is why we need to have a surface scalar field. Okay, so that is why this FBC flux of H by A is calculated here, and this is going to be act as means this is going to be input into the this pressure P equation that you are forming a matrix here. Okay, so this is the same equation. Okay, now you can see. Okay, now you can see here that this complete equation that I'm saying that means one upon, since we are calculating the inverse here, so that is why RAU equal to 1 upon U equation dot A. Okay, as I told you that HU, that term HU is equal to the FB minus all the terms of the neighboring terms. So that H terms we are calculating using the this U equation dot H operator. Okay, now we are multiplying with RAU, so these terms that we are getting here. Okay, Now in OpenFOAM, simpleFoam by default works for the py row. So we don't need to worry about the row here. So that is why you are not finding at the row. Okay. So this row terms you can exclude here. Now if you, this HB by H by A is a volume vector field. We need to calculate the surface scalar field because we need to put as a divergence term here. Okay, so that is why we have taken the flux of the this H by A. So this is the this term on the right side, and this is the left term on the left side. So this pressure is the Laplacian of the RAU into the this terms completely, because we are taking the Laplacian here. So delta into delta will become the Laplacian. Okay, and this is the means 1 upon U equation dot A. Okay, so now I think you know that what is this H by A. H by is nothing but U equation dot H, which is nothing but Fp minus this complete term, that is the neighboring term. So this operator is means specifically calculated in the OpenFOAM. Okay. So I think you have now better idea about the every algorithm. So you have any questions related to the simpleFoam, pimpleFoam or PISO form? Please let me know in the chat box. Anyone have any questions? So I've uploaded all the solvers here. I have also uploaded the blockMesh, and this folder I have suggested. I means study of AppSec has shown for the meshings. Now I'm going to upload today, and you can just visit this understanding the mesh folder. Please let me know if you have any questions. Because I think I have means my content is over for now. No one has any question? So if you have no any question, I think we can end the sessions. Tomorrow we have tomorrow is Sunday, but still we have a class. Okay, and please join at the same time. So speaking of how much character is required, means that depends upon your problem. For example, sometimes speaking of the non-orthogonal characters, sometimes it happens that it solves problem by taking only two value equal to two. Sometimes it, but just generally, I means whatever the problems I works generally is, characters equal to two means it is means you can say that. Uh, it is the normal value that you can take start with the 2, then go to the 4, then 3, then means, but beyond the 4 if you are going, then you are going to get the wrong solution. Your solution will be not accurate. So you can start with the 2 and you can go up to the 4. Okay, so number of characters is depends upon problem to problem, as I yes, Rupert. So tomorrow you will have a class that some portion is left for the C++ that we are going to discuss in the tomorrow class. So half class will be taken by the Nikhil, and second half I will take, that I will discuss the dictionary. Yes, same time, 8 to 10. Okay, so I think we can end the sessions. Yes, that is good questions. I think that for that to explain how non-orthogonality affect the solution, for that purpose I need to show you the one example by taking the means, by taking the geometry that I think I can include one or two slides in future sessions. That is good question. How non-orthogonality affect the solution, and how this non-orthogonality character is going to solve the problem. That I will include in one or two slides for these questions, Jamsi. See, I can give you basic idea. Like we take interpolation from cell center to face center. So if there will be, so we generally approximate the linear solution between the cell center to the face center. So if we are taking the distance between the cell center to face center, something suppose d. So this d is only valid if you have a north orthogonal meshing. If the meshing is not orthogonal, then we cannot calculate the this d value. In that scenario, we called it as a non-orthogonal problem. When the meshing is not perpendicular to the each cell, then there is an approach to calculate the this d value, and that is issue, that is something known as the non-orthogonal issue. So I will show you one example, maybe by taking one or two cells, and I will also show you that how this non-orthogonality iteration works in the OpenFOAM. Yes. Okay. So I think good night to all of you. Thanks for attending the sessions.